So this is the review of the practice test for the H2 Chem test on nuclear chemistry. First section, matching. So these are all essentially just definitions that you need to know, all the terms related to nuclear chemistry. The splitting of a nucleus into smaller fragments is called fission. That's choice J. This particle here, which has a charge of -1 and no mass with a little e, that is the equivalent of an electron, which is also called a beta particle when we're talking about radioactive decay. The process whereby a stable nucleus loses energy by emitting radiation is called radioactive decay. All radioactive decay involves losing energy in particles. A particle with the mass of an electron but a positive charge, so this is the opposite of an electron, it's called a positron. A particle with 2 protons and 2 neutrons, which also happens to have a +2 charge, is called an alpha particle, that's choice E. Isotopes that emit radiation because they are unstable, those are called radioisotopes, they emit radiation. The most penetrating of the 3 main types of radiation are gamma rays, or is gamma radiation, choice A. A device that uses a gas-filled metal tube to detect radiation is called a Geiger counter. The time required for half of the atoms of a radioisotope to decay to products is called its half-life. And the combination of 2 nuclei to produce a nucleus that is heavier is called fusion. So fission is splitting of atoms, or nuclei, and fusion is putting 2 smaller atoms together to make a bigger atom. So the multiple choice section. Which of the following is always true about radioisotopes? Well, the only answer here that is completely true all the time is choice A. They are all unstable. They do not generally have a 1-to-1 ratio. That would actually be fairly stable and not radioactive. And the products of radioactive decay are not always immediately stable. Sometimes it takes several decay cycles for a radioisotope to produce a stable isotope. So all of the above is not a choice either. Radioactive decay is spontaneous, occurs when unstable nuclei loses energy and does not require any input of energy. These are actually all true, so D would be the choice here because all 3 of those statements are true about radioactive decay. Which of the following has no mass and no charge? The only one here that meets both of those is gamma radiation. Alpha is positive charge, beta is negative charge, positron is positive charge, and alpha particles also have mass. When we have U-238, which is the isotope uranium with a mass of 238, undergoes decay by losing an alpha particle, the other product is, so let's do the equation out here. So you always set this up. 238 is the mass that you're given, uranium. If you look that up on the periodic table, it's element number 92. And it's going to decay by losing an alpha particle, which we represent as 42He. Well, the other product is what's left over when you take away an alpha particle from the element that you started with. So I took 4 away from the mass number, so my new mass is going to be 234, and I took 2 away from the atomic number, so my new number is going to be 90. If you look that up on the periodic table, it's thorium. So the choice here is B, thorium-234. When radon-222 undergoes decay to become polonium-218, it emits. So this is kind of going the other way around. It's not specifically telling us what type of decay this is, but we know it starts out as radon-222. Radon is element number 88. And one of the products is 218 polonium. Polonium is element number 86. Well, that tells us, just like in the last example, we lose 4 from the mass number and 2 from the atomic number. That is called an alpha particle. Choice A. Which of the following is true concerning a plot of the number of neutrons versus number of protons? So if you draw a graph with neutrons on one axis and protons on the other, and you draw a line, there is a band of stability where all the elements that fall along that line and it starts down near the 1 to 1 and then it actually goes up a little bit, they will all be stable. And then if your nucleus is outside of that band of stability, it will decay. And where the atom falls in that graph can also tell you what type of decay it's most likely to undergo. So the choice here is actually all of the above. All of these statements are true if you draw a plot of proton to neutron ratio. Alpha emission. So now we're back to talking about that plot. So we've got this line and the band of stability, and then we've got alpha emission. Which group of atoms is it? Group A, if we had group A to the left of the band of stability over here, would that be alpha emission? No, it wouldn't. Over there would be beta emission. Okay, so this is going to be beta emission over here. Down here you've got electron capture and positron emission. Alpha decay actually takes place over here, and the reason it takes place over there is because it actually increases the ratio of neutrons to protons. And you could do the math out to figure this out. It's only a slight increase, but by spitting out 2 protons and 2 neutrons, the ratio of protons to neutrons goes up slightly. The alpha decay occurs with the really heavier elements. So the choice there was B. Which of the following is true about half-life? It measures the decay of radioactive isotopes. That's certainly true. The shorter the half-life, the more dangerous the radioisotope. Not necessarily. Half-life predicts which atoms in a radioactive sample will decay? Absolutely not. Okay, so we know it's not going to be all of the above, because the only one that's true here is A. Half-life measures the rate of decay. That's the term we use for measuring the time it takes for half the sample to decay. The transuranium elements. So transuranium means all the elements above atomic number 92, so everything past uranium on the periodic table. Okay, they are all atomic numbers above 92, that's correct. They actually do not occur in nature as far as we know. None of the elements heavier than uranium have ever occurred in nature. We've made them all here on Earth, which means that not all of the above is true. And sometimes radioactive? No, they are all radioactive, so the choice here is A. If you bombard nitrogen-14 with an alpha particle and you get one product, what would it be? Well, let's set up the equation again. 14, 7, that's nitrogen, atomic number 7, plus an alpha particle. So again, the key to remember with all these nuclear equations is that the numbers on the top and the numbers on the bottom have to add up to the same total on both sides. So if I add 14 and 4, I get 18. If I add 7 and 2, I get 9. And it's not nitrogen 18 over 9 because number 9 is not nitrogen. Number 9 is fluorine. So that would be choice C. And the other ones just don't work out numbers-wise. So this is fluorine. You'd have to look that up on the periodic table. Which of the following is true about gamma radiation? The mass number decreases by 4. The atomic number decreases by 2. The atomic number increases by 1. And neither the mass nor the atomic number changes. Well, gamma radiation does not affect the mass or the atomic number. These first two choices have to do with alpha decay, and the third one is beta decay. So the choice is D. These are not correct. D, though, is correct for gamma radiation. Nuclear reactors use controlled fission to produce energy, use neutron moderation to absorb and control chain reaction, cannot produce a nuclear explosion, or all of the above. These are actually all true. You might think that a nuclear reactor, if it has a meltdown, could produce a nuclear explosion. But the fact is, nuclear reactors do not have what is called the critical mass to create a nuclear explosion. They can certainly create other types of explosion because of the gas that's produced if it overheats. That's what happened in Chernobyl. The hydrogen gas that was produced during this meltdown process then ignited and created an explosion, which can then spread radiation and radioactive material, but it's not in fact a nuclear explosion like an atom bomb. To do an atom bomb, you need highly concentrated, what's called critical mass of an isotope to do this very fast chain reaction all at once. Nuclear reactors don't have that critical mass, but these other three things are true. So choice D. Which is true about nuclear fusion? It releases more heat than nuclear fission. It involves splitting nucleus into smaller fragments. It can occur at room temperature, or all of the above. Well, it is not all of the above. because although the dream would be to create fusion at room temperature, it is not possible at this point. And fusion is fusing atoms together, not splitting them apart. Splitting them apart would be fission. So the only choice that's correct here is A. Which of the following is true concerning radioisotopes? They can be used as tracers to study chemical reactions and molecular structures. They can be used to diagnose certain diseases. And they can be used to treat certain forms of cancer. Those are all true. Radioactive isotopes have a lot of uses that are conducted every day in medicine and other types of science, because we can very easily find them using different imaging technology. And if we use stuff with very short half-life, which means it decays very quickly into something stable, then it can be put into your body and it either gets passed out very quickly or it just decays into something benign in a very short period of time, so it doesn't really damage your cells. But it can be used to damage cancer cells if you put it in the right place, and it can be used to trace movement of different types of particles in your body and to trace chemical reactions, so D. All right, some problems. These are nuclear reactions where we're going to fill in the blank. So radon-226 and atomic number 88 decays, and it, that's radium, and it produces radon and some other particle. That particle has a mass of 4 and an atomic number of 2. We put He there for a helium nucleus. That is an alpha particle. The numbers that go with radon are the difference between the 226 and the 4, which would be 222. And on the bottom we have 88 over here, and we have 2 already, so we only need 86 more. So again, remember, the numbers on this side have to add up to the numbers you started with. And sometimes you might need a negative number to make that happen, which we're going to see in another example. So if we have protactinium-234, which is number 91, and then that becomes uranium-234, which is element number 92, what is the other part of this equation? Well, we didn't change the mass number, so in order to keep the mass the same, I add 0. But I did increase the atomic number. The only way to make that work on both sides is if I have a negative 1. 92 plus negative 1 equals 91. So a negatively charged particle with no mass is an electron or beta particle. And finally, thorium-234. Well, thorium, if you look it up on the periodic table, its atomic number is 90. So that's the first blank. And then over here, one of my products is a beta particle. The other product I need to figure out. I didn't change the mass number because on this side I have a 0 so far, so 234 is still my mass. And I've got a negative 1. Well, what plus negative 1 would equal 90? 91. And if I look at that up, that element, number 91 is protactinium, symbol Pa. So if the half-life of protactinium-234 is 6.75 hours, and you start with 12 grams, how much will remain after 27 hours? So if we use the formula, the amount remaining equals the starting amount times 1/2 to the power of the number of half-lives. And then we start plugging in. The amount remaining will be 12 grams times 1/2 to the power of the number of half-lives. But how many half-lives have gone by? Well, 27 hours have passed. Each half-life is 6.75 hours. So that means that 4 half-lives have passed if you divide 27 by 6.75. So 12 times 1/2 to the 4th power gives you 0.75 grams. The other way you could have done that once you figured out the number 4 for half-lives is said, I start with 12 at 0. After 1, I have 6 grams. After 2 half-lives, I have 3 grams. After 3 half-lives, I have 1.5 grams. And after 4 half-lives, I'd be down to 0.75 grams. So you get the same answer either way when it's, again, when it's a whole number and a relatively small number like 1 through 5. You can do this method where you just divide it in half a certain number of times, or you can always use the formula. Either way will work there. After 71.5 years, a 4-gram sample of phosphorus 32 has decayed to 0.125 grams. What is the half-life? So we're kind of working backwards here, and we're given the starting amount, the remaining amount, and the elapsed time. What we're not given is the half-life. So the simplest way to do this, and we can try it, is to say if I start with 4 grams at time 0, I would have 2 grams after 1 half-life, 1 gram after 2 half-lives, half a gram after 3 half-lives, a quarter of a gram after 4 half-lives, and I'd get to 0.125 grams at 5 half-lives, and that's the amount remaining. The question, though, wasn't how many half-lives. The question is how long each half-life was. So in order to figure that out, I have to take the amount of time that has passed, 71.5 years, and divide it by the number of half-lives that is. And I get 14.3 years is equal to 1 half-life. 14.3 times 5 is 71.5 years. So this is the final answer here. 14.3 years is 1 half-life. An alpha particle collides with thorium-230 and produces krypton-92, 3 neutrons, and a new element. So this is slightly different from the equations we did a little earlier, but the process is going to be the same, or the principles are the same. So we're told we have an alpha particle, and that collides with thorium-230. Thorium is element number 90. It produces 3 things. So we've only so far really had 1 or 2 things on each side. Now we've got 2 on one side and 3 on the other. But the process is the same. The numbers have to add up on both sides. So the first thing it tells us is we have krypton 92. Krypton is element number 36, and it says 92 because that's the mass number they give us up here in the question. And 3 neutrons. Neutrons have a mass of 1 and no charge and no effect on the atomic number. So what does that mean? That means that if we add up the numbers on the top left side, it would be 234. So we take 4 plus 230. If we add up the bottom side of this side, it's 92. Those aren't the numbers we're going to put on the right, though, because we've already taken some of that with the 92 that's up here for krypton. We've already taken 36 from the atomic number with krypton. We've also taken 3 neutrons. Each one of those is worth 1 to the mass, so that's a total of 3 for the mass. But there's no effect on the atomic number. So now we need to work out what does that leave us on the top and the bottom. Well, 234 minus 92 minus 3 is 139. So that's going to be our top number in our last product. And then 92 minus 36 is 56. So that's our bottom number, the atomic number of the new element. And if you look, atomic number 56 is barium. So now, go back and look again. You've got 92 plus 3 times 1 plus 139. That adds up to 234, which is the total on this side. And you've got 36 plus 0 plus 56, which adds up to the 92 you have on that side. Okay, an atom of plutonium-242 is produced when calcium-40 collides with another element. So we're doing the same type of thing here that we've done in the previous ones, where we're given some of the parts, and then we have to fill in some blanks to make sure all the numbers add up on both sides. So plutonium-242 has an atomic number of 94. Over here we've got calcium-40. It's element number 20. Well, it doesn't say there's any other particles, any protons, neutrons, alpha particles, anything else. So everything else that gets us from calcium-40 to plutonium-242 has to be this other element. So the first thing is, well, what's the difference in mass? 40 to 42, the difference is 202. 20 to 94, the difference is 74. So I've got some new other element that's colliding with calcium that's got a mass of 202 and an atomic number of 74. And if you look up atomic number 74, it's tungsten, which has a symbol of W. Okay, essay question. Distinguish between the chemical reactions and nuclear reactions in terms of the following. Okay, the driving force behind the occurrence of each. Well, the driving force behind chemical equations is the need for elements to have full outer shells of electrons. Okay, so any elements that don't have full outer electron shells are going to beg, borrow, or steal electrons in order to get their outer shells full. So that's what drives chemical equations. It's the electron configuration and elements that need new electrons or want to get rid of electrons in order to become more stable with an outer full shell. The driving force behind nuclear equations or nuclear reactions is the stability of the isotope, which is driven by the proton to neutron ratio. Okay, so nuclear reactions are driven by the ratio of protons to neutrons in the nucleus. Anything that is not within the band of stability generates instability, which leads to radioactive decay in nuclear reactions. For chemical reactions, you're talking about instability that's caused by an incomplete outer shell of electrons, and then the elements are trying to either get rid of or add electrons in order to either strip off an incomplete outer shell or fill an incomplete outer shell, and that's what makes chemical reactions go. The relative amounts of energy involved in each. This is pretty simple. Nuclear is greater than chemical. Again, it's the comparison between a stick of dynamite and an atomic bomb. When you consider the amount of material that's used to make a stick of dynamite and the amount of material that's used as the heart of an atomic bomb, they're actually not that far off in terms of the amount of material, but just think about the difference in the power of a stick of dynamite versus an atomic bomb. Much, much more energy from nuclear equations. The products generated by each process. And by this we're talking about, well, what happens during a chemical reaction versus a nuclear reaction? In a chemical reaction, you get new compounds, new substances, or different substances. Okay, sometimes maybe you started out with a compound, you end up with a group of elements that are separate. Okay, so it doesn't have to be a compound, but you've got different substances. But the key here is with a chemical, you have the same atoms from start to finish. They just get moved around and combined in different ways. In a nuclear reaction, you actually get new elements. Okay, the elements themselves change. The atoms split or fuse together to form different elements. The atoms are not the same from start to finish in a nuclear reaction, whereas the atoms in a chemical reaction just get moved around without changing the actual atoms. So just have an understanding of this. Also, you want to take a look at the main components and functions of a nuclear power plant. How does that work? We watched some of that in the video with Bill Nye. So take a look. It's in your book in chapter 25. And just have a basic understanding of what makes or how a nuclear reactor generates electricity from the nuclear material to the electricity coming out the end. What is the process in at least a basic way?